So first of all, it's a real honor to speak here. First time I've been at LambdaConf. And a word or two about me. I'm a retired math professor. And since I retired, I have more time to do lots of fun things. And one of them is to dabble in programming, functional programming in particular. My first experience with computing was, I hate to say this, probably around 1966, when I had a summer job doing some stuff in numerical quantum mechanics, and I had to learn Fortran. I had to punch my own cards, put them into the card reader. The development cycle was so slow, it was incredible. And I also had to work from midnight to 6 a.m. because that was the only time I had access to the machine, which was an IBM 1620, which probably went from here over to here. And I think I OD'd. I didn't touch a computer for many years after that, but eventually I found my way back. So anyway, what I would like to talk about is the MiniLaTeX project. And the aim of it is to bring LaTeX to the browser. So you can read more about it if you want at this website. LaTeX is an elaboration of TeX, which is the creation of the noted computer scientist Donald Knuth. It's the tool that all mathematicians, computer scientists, physicists, and other geeky species use to write their articles, their class notes, and their books. So let me talk a little bit about what is involved in this. So LaTeX is a markup language. Let's see, maybe I should see who knows what here. Raise your hand if you're a LaTeX user. Okay, so I'll say the requisite thing. So LaTeX is a markup language like Markdown or AsciiDoc, but it has some very sophisticated features for rendering mathematical text. And by the way, when Donald Knuth was developing this, he spent an incredible amount of time learning about how fonts are built and sort of the aesthetics of it. And one of the great things about, and this goes to the core of it, which is TeX, one of the great things about it is the aesthetics are just amazing. Before I started using TeX, I used some horrible equation editors, and they were painful to use, and they also didn't give very good results aesthetically. So anyway, it's a specialized markup language. There's an example of a little piece of LaTeX. When rendered, it looks like this, a familiar formula from calculus. Here's another little piece of LaTeX. When rendered, it looks like this. These are the two kinds of LaTeX source text. There's math mode text, which is the text between dollar signs, the formulas and whatnot, and then there's the rest. Okay, so math mode text and text mode text. So the typical way that you operate when you're writing something in TeX or LaTeX is you have a text editor, you create your document, you edit it. From time to time, you run it through a program like PDF LaTeX, which renders it. You can see if you've made some mistakes, whether it looks okay. It's also what you use to produce the final printed document or the one that you share on the web. But these days what you would like is a way of rendering your source text directly into HTML. And there are ways of doing this. There's MathJax, for example, which gives quite high quality aesthetics for the math mode text. And most blogs that people run with math content use something like this. There are also tools like Pandoc, which is a batch processing program. It actually processes many kinds of markup languages, including LaTeX, and produces rather good output. But I would like to do something a little bit different. In particular, I would like to have a way of live editing LaTeX. So let me, let's see, let's see, what do I, I have to click on that. This is not, okay. So I'm going to go to a little demo app. And it probably happened a little too fast for you to notice, but okay, on the left-hand side, in the left window, there is some LaTeX source text. Let me scroll down here to where you see some equations. Let's say, click on this. There is some commutative diagrams, okay? Down here, there's some chemical formulas. Up here, there's just some plain old math formulas. So, you may wonder, this could be a fake demo. So let me copy a couple of the formulas. Let me clear the editing window, and I'm going to paste them back in, and I want you to see how long it takes to render it. So ready, set, go. So it's rendered. Okay. Of course, that's a small amount of text, so maybe that's not too surprising. But let me show you another example. I'm going to click on the example 2 button below. What it's going to do is it's going to load some source text into the left-hand window, and then we'll see how long that takes. So ready, set, go. Okay, there it is. Okay, and now let's edit it. So I'll change 1 to 100, which is rather odd for a probability function, but we'll do it anyway. So once again, it renders quite quickly. So this is what I mean by live editing. Notice, by the way, that okay, let's go back to, well, let's restore that formula to its original state, and let's extract it here, and let's clear it. Let's see, what was it that I wanted to say? Ah, yes, in the input window, you don't have to put begin doc and import this and import that. What we're dealing with here is a sane subset of LaTeX. So my aim was to create something that I could use for things like lecture notes, even little research notes and whatnot. So it's not going to do absolutely everything, but it's going to be good for many, many common uses. And it's quite convenient because, look, I don't have to set up all that stuff. Yes?
I'm sorry, I really mentioned.
That's okay.
How are the formula rendered?
Okay, well, that's the subject of the talk. I'm just giving a demo, but I'll get to that in a moment, yeah. So, in fact, back to the slides, and we'll see how to do that. So we would like a live editing system. We would like something where we have immediate content delivery. So you write your thing. When you think it's ready to share with your students and your colleagues, you press some button to make it public, and that's it. Okay, you don't have to do anything else. You also would like to have some sort of a searchable document repository, because you write this thing, you don't want it to disappear when you turn your machine off or go to a different web page. And you want the document repository to be searchable so people can find things by title, by author name, keywords, etc., even full text search. Okay, so here's an example of such an app. This is kano.io, K for knowledge, sort of cheesy, but that's what it is. These are some lecture notes for a course I taught a little while ago. In the left-hand column, you see a table of contents that actually points to a bunch of separate documents, kind of like when you have a LaTeX document, you have an input file that brings various things in. In the center column, you see the rendered text. Let's see, there we go. And what you see there is the reading mode of the app, so that little red button up there that says read. If you want to edit it, you go to somehow the bar doesn't show quite the right thing, but anyway, the middle column now is the source text. Okay, the right-hand column is the render text, like what you saw in the demo, and you see various elements. There's a subsection macro. You see it rendered on the right with an automatically provided number. There's an image macro. It takes just 3 arguments: the image URL, a caption, and some information about size and positioning. That's, by the way, a little macro that I wrote specially for this package, but you can export any MiniLaTeX document, and when the export function sort of munges things around and provides whatever small changes you need, so it's standard LaTeX. It can be run through any LaTeX processor, PDF LaTeX. And then, of course, math mode stuff. Okay, so the question now, and this will eventually answer your question, is how do we render LaTeX to HTML? So there are various answers to this question. The most general and least informative is through the miracle of typed functional programming. Okay, we're also going to use division of labor. If MathJax or some similar tool did not exist, I would never have contemplated this project. So MathJax is going to take care of the truly hard part, which is rendering the math formulas. And MiniLaTeX is going to take care of rendering the rest, the text mode LaTeX. To render the text mode stuff and to pass the math mode stuff on to MathJax, we're going to divide the work into 2 phases. We're first going to parse the source text into some intermediate representation, an abstract syntax tree. And then we're going to render the abstract syntax tree. So the first part, the parsing, is actually the hardest to accomplish. It was hardest for me. The rendering turns out to be, well, it takes some work, but it's sort of routine. We're going to parse using what are called parser combinators. So this is a way of building up a recursive descent parser from the bottom by starting with elementary parsers, combining them in various ways, combining those, and so forth. And the parser library I'm going to use is Elm/parser. The two apps that I show you are both written in Elm. It's a great language for building front-end web apps. And it turns out that its parser library has the mojo that's needed to write a LaTeX parser. So let's try to flesh this out a little bit more. There's a little piece of LaTeX text. We want to render it like that. We're going to go through this intermediate step of creating an abstract syntax tree, and then we'll render that. Okay. So the question now is, what's an abstract syntax tree? So I sort of remember this from studying some computer science book someplace, but I had to refresh my memory on all this before I started on the project. So the first thing I did is I looked up some stuff in Wikipedia, and I found something kind of like this. So I'm going to explain it by thinking about the English sentence, Alice eats oranges. And you see that sentence as the bottom level of a little tree that has red nodes and black nodes. The red nodes are the non-terminal nodes of the tree. Non-terminal nodes, by definition, have children. Terminal nodes, by definition, do not. Okay? So we're going to build this tree up step by step, and then I'm going to elaborate these steps in a moment. So we begin with a start symbol, or a starting node, sentence, and that can be expanded to the next level of the tree, subject followed by verb followed by object. And then each of those non-terminal symbols can be expanded or derived into terminal symbols. Alice eats oranges. So there you see the sentence at the bottom. So the production of this tree is governed by a formal grammar, and I want to describe that now. Formal grammars are to define a formal grammar, you give a set of what are called production rules, which tell you how to take certain symbols and replace them by other symbols. Okay, so it's a symbol processing game. So the first production rule for this tiny microscopic grammar for Alice eats oranges is a sentence can be derived to a subject followed by a verb followed by object. If you diagram sentences in high school, this will seem familiar, and I did have to do that, and I thank Mrs. Lee for making me do it. So the next rule is a subject can be derived to either Alice or Bob. This is a very, very small grammar. But here you already see the two main aspects of production rules. One is you derive a symbol to a sequence of symbols, one after the other. Another is you derive a symbol to one of several alternatives, in this case only two. We have a rule for deriving verbs and for deriving objects. And we can sort of visualize the whole process like this. We begin with the start symbol, a special non-terminal symbol. We apply the only applicable rule. We get subject followed by verb followed by object. And now we have some choices, but I'm just going to do it in left to right order. I apply the subject rule and choose the first alternative. Then I apply the verb rule. Well, I also choose this first alternative. And finally, I apply the object rule, but choose the second alternative. And now I stop because I have only terminal symbols and there's nothing left to apply. So, this already gives you some fun stuff to do because you can, maybe with a little bit more elaborate grammar and, well, even with this, but with more alternatives, you can construct sort of random sentences that make perfect grammatical sense. They may be meaningful sentences, they may be whimsical, they may be nonsensical. Okay, so a grammar is a set of production rules. Let me give you another example. I realized I sort of cut down everything for a 40-minute talk, and then I realized it was 50 minutes, so hopefully this all works out. So let's think about identifiers in a computer language. So these will be things that start with a letter of the alphabet and then are followed by 0 or more either letters or numerals. Okay? So simple as that is, it's described by a small grammar. The first rule is that an ident, which is the start symbol, can be derived either to an alpha or a tail. And I'll explain these as we go along. A tail can be derived to one of three possibilities: an empty string, alpha followed by tail, or num followed by tail. Alpha, well, that can be derived to a letter of the alphabet, and of course you guess what's coming next. Num can be derived to 0 or 1, or, well, the numerals 0 through 9. Okay, so let's derive an identifier. So we begin with the start symbol. We apply the only applicable rule, which is 1, and we get alpha tail. Let's see, what can we do next? Let's apply rule 3, which will transform alpha to one of several alternatives, and I choose A. Okay? Then we're going to derive tail again. Let's do this, alpha tail. Okay? And then we're going to derive alpha tail using rule 3 to another letter, say B. Okay? It's getting a little tiresome, but let's finish it up. We'll derive tail using rule 2 again, but this time to num tail. And finally, we will derive num to, well, almost finally. Penultimately, we will derive num to the numeral 7 using rule 4. And then to finish up, we derive tail to the empty string using rule 2. So now we have a list of terminal symbols. We can concatenate them. There's our identifier. Okay, so I think, even if you haven't done this before, you sort of have a pretty good understanding now of what a formal grammar is and how you apply it to generate things. So to summarize, a grammar G is a set of production rules. Using production rules, you can generate an abstract syntax tree. The terminal nodes of the abstract syntax tree, read in the correct order, gives you a sentence in the language specified by the grammar. So apples, Alice eats oranges, or AB7, whatever it was. Okay, so those are examples. So now the question is, what's the grammar for MiniLaTeX? Okay, so this is going to be the first stage in defining a parser and then a renderer and then building these apps. So Mrs. Grundy says to me this: you should first of all think about what the type of the abstract syntax tree is. So it's going to be a union type. It's going to have various components. And the way I set about doing this is I just thought about, I've used LaTeX ever since I was a child almost. Ha 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 ha. And so I just thought about the different kinds of LaTeX things there are. So well, first of all, I baptized it. I gave it a name. It's going to be LaTeX expression. And the first component is going to be the thing that captures ordinary text. Okay, so that's going to be an LX string. So the components of this type have payloads, and the payload here is the English string that you see on the right, once upon a time. You have inline math text. That's going to be captured by that sort of element. So again, just a string payload, but with a different identifier, or a constructor, I should say. Display math, same deal, except that the math text is enclosed by double dollar signs. You have macros, like you might have an italicized piece of text. A macro consists of backslash in the macro name, and then a possibly empty list of arguments, where the arguments are enclosed by curly braces. So that is going to be captured by macro and then some arguments which constitute the payload. String will capture the macro name, and the list of LaTeX expressions will capture the argument list. Notice, by the way, that this is already a recursive type because I'm defining LaTeX expressions in terms of LaTeX expressions. The next one, which is the most fun of all, are environments. So, you might have backslash begin theorem, blah, blah, blah. The blah, blah, blah is the body of the environment, and then followed by end theorem. And that's captured by this part of the type. Environment, string. The string captures the environment name, and then LaTeX expression, which has to be further elaborated, captures the body. You have LaTeX lists. A paragraph will consist maybe of some text, a math element, some macro like italic, wow, this is such a great theorem, and so forth. So you have to have a way of representing lists of LaTeX elements or LaTeX expressions. You have comments in TeX. So they are represented this way. You have itemized lists. You've got to capture their elements. You do it that way. And sort of a new feature of MiniLaTeX is that you can define, just like in ordinary LaTeX, text mode macros. So \new command, the macro name, you have to specify the number of arguments, and then the body of the macro. So that's captured this way. New command, string for the name, int for the number of arguments, and LaTeX expression for the body. And then finally, you have to be able to capture parse errors that are generated along the way. You know, we all make errors. And the aim there is, first of all, to keep going, and secondly, to, in the rendered text, to represent the errors in some nice way so that you know what's going on. Okay, so typically I render them in red, so they're easy to spot. Okay, so given this, let's think about some fragment of the MiniLaTeX grammar. So the top level production in the grammar is going to correspond essentially one-to-one to that type definition. So we had the type LaTeX expression. Okay, it's on the previous slide. And remember, it was a union type with various components: inline math, display math, and so on. So this production, the first production in the grammar, just reflects that type definition. And then, of course, you have to figure out how the non-terminal symbols that appear on the right are going to be expanded. So, for example, display math, that's an easy one. Any math stuff enclosed in double dollar signs. Macro, well, let's see. Macros have a name, and they have a possibly empty argument list. So you're going to have non-terminal symbols for those things. It all kind of sounds like wishful thinking, but you know, it all works out because you keep expanding until you get down to terminals. Environment, I'm not going to list them all. In fact, this is all I'm going to list. The environment production is an interesting one because there's something different about it. Notice that there's both red and black on the left-hand side. So on the left-hand side of the production, you have both non-terminals and terminals. So env name stands for, it's a string, and it can be the name of any environment. It could be theorem, it could be definition, it could be joke. It's actually not limited, okay? So that will derive to the beginning phrase for an environment. I mean, environments always begin with begin, environment name in curly braces. And then there's the body, so that has to be parsed. That's going to correspond to LaTeX expression. Again, you see the recursivity of things. And then it ends with that ending phrase, \end, environment name in curly braces. So there's a little fragment of the grammar. Now let's see how this relates to the abstract syntax tree. So on the upper right, you see a piece of LaTeX source text, and I'm going to show you the corresponding syntax tree, which is compatible with this grammar that I began to sketch. So we begin with a start symbol. The macro strong Newton is going to produce this left-hand branch of the tree. Notice the subtree headed by macro. It has two children, the name of the macro strong, and then the body of the macro, which goes just down to Newton. The English text says corresponds to that little short middle tree, and then the phrase that begins with begin theorem is going to produce the right-hand branch of the tree, a subtree headed by environment, which has two children, the theorem, which is the name of the environment, and then LaTeX list, which is the beginning of the body of the environment. So that will derive to all of this stuff, okay? So once again, you see that if you sort of read it in the right way, kind of looping around like that, you read off the original piece of LaTeX text. So that's great. You can, you can play the same game that I played with Alice Eats Oranges. I could use the production rules to generate arbitrarily many uninteresting abstract syntax trees and legal pieces of LaTeX source text. But what we want to do is the opposite. We want to start with source text, and we want to build an abstract syntax tree which represents it. And like most problems in mathematics, if there's an inverse problem that makes sense, it's usually more difficult and more interesting than the problem itself. So that's what parsing is. It's sort of an inverse to the application of production rules. I think of a parser as a little machine or a little animal that eats characters one at a time, building up something, in this case an abstract syntax tree. So let me talk about how this works. They're going to be, on the one hand, elementary parsers, and on the other hand, they're going to be combinators which are used to build up more complex things. So I'll give examples of 4 elementary parsers. The first one is the symbol string parser. So it takes a string as an argument. It produces a parser for the unit type. If I run the symbol A parser on the string ADX blah blah, the parser succeeds and it returns OK unit type. So this just signifies that the parser succeeded. It doesn't return any information. It just tells you that it succeeded. On the other hand, if I run it on the string WDX, it fails and it gives me a list of parser error messages. Okay, so if you get into the technical stuff, the return value of running a parser on a string is a result type, and it's either a list of parser errors or it's a value of the kind that you were seeking. Another useful parser is the float parser. If I run float on the string 1.2, sure enough, it returns a floating point number. The spaces parser just chomps away arbitrarily many spaces, including no spaces at all. So if I run it on that string, I get OK. The last elementary parser I'll introduce is the succeed parser. This is a weird one. It takes a value of any type and returns a parser for that type. And it has the unusual property that if I run it on anything, it always succeeds and it always returns the argument that was used to construct the parser. So if I run succeed string A on the string A, it returns OKA. If I run it on the string B, it also returns the same thing. If I run it on the string ho ho ho, it's Christmas time, it still returns OKA. Okay, so now let's look at parser combinators. So there are going to be 2 kinds corresponding to the 2 ways of building up production rules. There are parsers for alternation and parsers for sequencing, or combinators for alternation and combinators for sequencing. So the alternation parser of interest to us is the one-of parser. It takes a list of parsers as arguments and returns a parser. So for example, if I feed one of the list symbol A comma symbol B, I will get a parser that will recognize strings that beginning with A or with B. But it will not recognize strings beginning with C or any other letter. Okay? The first sequencing parser I want to look at is the pipe dot parser. It takes 2 parsers as arguments and returns a third parser. It's used like this. I'm going to, for example, combine the float parser with the spaces parser. And what it will be able to do, it can chomp a floating point number like 1.2, chomp some spaces, and it'll return the float value. So it's used to sort of ignore certain kinds of successfully parsed input. So if I run float pipe dot spaces on 1.2 spaces ABC, it returns OK 1.2, and it's parsed all the way up to the character A. Okay? So then maybe other parsers will take on from that point. Okay? The second sequencing parser is pipe equals. It also takes 2 parsers as arguments. The first one is a bit hard to get your head around. It's a parser for a function of type A to B. So I'll try to explain this by means of an example. And the example is we're going to parse a point. Okay? Now I'm going to represent points in Elm by a record with 2 fields, X and Y, both of which are floats. And whenever you define a record in Elm, you get for free a constructor function. So point is also a constructor that will take 2 floats as arguments and produce a value of that type. Okay, so if I form the value succeed point, that is going to be a parser of type float to point. And I'm going to use that in the next slide, and you'll see what's going on here. So in real life, a point might be represented by, say, 1.3 space 4.7. And that's described by a little mini grammar like this. The non-terminal point goes to float, followed by spaces, followed by float. Maybe I should have put those in red or something. A parser for that kind of thing is going to be constructed out of parsers for points, for floats, for spaces and floats. I just put those parsers in order, and I combine them using either pipe dot or pipe equals, depending on whether I want to keep the result of parsing or ignore it. So if I run that parser on 1.3 space 4.7, sure enough, it parses that and gives a value of the expected type. So, by the way, to see that this really works, you might want to think about the types. I've written the parser pipeline out with a little more space. I've written underneath the types of the different parsers, abbreviating float as F for space reasons and point as PT. And so there are all the types. And now I'm going to combine them two by two and see what happens. So if I combine the first two parsers using pipe equals, I get a parser of type F to point. Okay, unfortunately, there's blackboards are better than slides for some things. Unfortunately, the definition of pipe equals is a slide back. So anyway, you sort of collapse the float to point by combining these things. If you now compose this using pipe dot with the spaces parser, you get a parser of the same type. And if you combine that using pipe equals with the parser of type float, you collapse once again and you get a parser of type point. So, you may have to goes by kind of quickly, but it is correct. It's not fake. So the important point here is that you can read off the parser definition from the production. So there was the production for points, and there is the parser. Okay, so just keep this rule of thumb in mind because it'll guide everything that we do. I'll give one more little example because you'll see in a second. So here's a slightly more elaborate and more conventional way of representing a point in the plane. There's the associated grammar. A point gets derived to a sequence of things, left paren, space, float, etc. According to my rule, I should be able to write down a parser definition for this by just reading this definition and translating it in the right way. So I'm going to begin with succeed point. That corresponds to the left-hand side of the production. And then I'll write down my little parser pipeline. I'll parse a symbol, left paren. Let's see there we go. Parse some spaces. So you see every click corresponds to an element on the right-hand side of that production. Parse a float, parse some more spaces, eat a comma, eat some more spaces, parse a float, eat some spaces, eat a right paren, and I've got it. So it's an almost mechanical procedure for writing down the parsers. So with this in mind, let's get back to work and see how this applies to MiniLaTeX. So the top-level parser is going to correspond to the top-level production. And we see on the right-hand side alternation, so we know that this parser is going to be built using one of, and it's going to be a parser for LaTeX expressions. We start with one of, and one of accepts a list of parsers, and the list is a parser for each thing that you see on the right-hand side of the production. So it seems like we're doing nothing, and in a sense we are, because display math, inline math, macro, etc., those are all parser functions which you have not yet defined. But it's sort of describing a work plan for you. So there it is. That's the top-level parser. Let's look at one or two of, let's go down the rabbit hole just a few steps and see what we have here. By the way, I should say that the parser is really a tiny piece of code. When I first did this slide, it was 334 lines long. It's maybe 400 lines, no more than that now. So it's a small but sort of delicate piece of code. So let's look at the macro parser. So parse things like that. There's the associated production and the grammar. So I'm going to read across and use that to write down the parser definition. This parser is going to take a parser for white spaces as arguments. And the reason for that is I can use it then in situations where white space means spaces, and also in situations where white space means either spaces or new lines. Okay, so we begin like this. We begin with succeed macro for the left-hand side of the production, and then we write down the pipeline. So macro name, the list of arguments, and the white space, and that's all there is to it. Okay, so it's sort of miraculous in a way. So the last one I will look at is the parser for the environment, because that was the thing, I should have mentioned this, because of the fact that the production contains both terminals and non-terminals on the left-hand side, the grammar for MiniLaTeX is not context-free. So that means that, you know, some standard parser tools, parser generation tools don't apply to this grammar. Anyway, the environment's going to be parsed by putting together two parsers, one that will parse the name of the environment and the other that parses the body. So, and pipe into and then is really just a way of saying pipe equals. So it's something we've seen before. So the environment name parser works like this. It's going to parse a string. We begin with the usual succeed business. And then we're going to parse but not care about the string \begin left curly brace. Then we parse a word, which is like theorem, for example. And then we parse but don't care about right curly brace. So that's all there is to it. That was maybe too fast, but there we are. What about the environment body? That's going to be a parser that takes a string as an argument, namely the name of the environment, which is provided to it by the env-name parser. So it's going to be the same deal. It's starting to get boring now, so we have to move on pretty soon. So the first thing we're going to do is construct the ending phrase for the environment using the argument that was supplied by the previous parser. So remember, all environments will end with \end, the environment name in curly braces. So we construct that phrase, and then once again, a little parser pipeline, beginning with succeed, parse some white space in case we put that in, parse the body, which is going to be a non-empty list of LaTeX expressions, parse any additional white space that we might have put in, and then end with symbol end phrase. We parse that, but we don't care. We eat it, so to speak, but we don't care what it is, just as long as it's the right thing. Okay, so once again, the environment parser is just something that we get by composing two parsers using one of these combinators. Let's see how much, I think I'm okay. So I want to say a word about the M word, because people sometimes ask about this. You know, one criticism of Elm is that it's not Haskell, but why should it be? Because we have Haskell, which is another great language. So Haskell has monads. 10 minutes? Okay, great. Okay, thanks. So there are monads in M. I'm going to go very quickly through this. There is the and then combinator, or there is the same thing written by replacing parser by M for monad. There's the bind operator in Haskell, and notice that they're the same thing up to permuting the arguments. So yes, Dorothy, Elm does have monads. Okay, let's skip all of this junk, because I just put it there in case I needed some padding, and I don't. So let's finish up by talking about a few other topics other than parsing. So we've got the AST. We now need to render that into HTML. And it turns out that there's sort of a recipe for doing this. We're going to have one rendering function per non-terminal symbol in the grammar. So we're going to have a set of mutually recursive functions that cooperate to produce the HTML. So I'll show you a couple of these. Let's see, what on earth is going on there? Ah, yes, okay, I remember now. So the top level production is that one. A LaTeX expression derives to one of a bunch of things, or a bunch of alternatives. So therefore, the top level rendering function is going to be implemented via a case statement that accounts for those different alternatives. Now, what about the arguments to the rendering function? The first one, LaTeX state, is something we haven't talked about. The second one, LaTeX expression, is something we've seen a lot of. That is the AST, that's the result of parsing. LaTeX state think of it as a dictionary that has information that is gathered during parsing, information about section numbers, cross-references, etc. So here's how it's going to work. We are going to have a case statement, one for each thing on the right-hand side of that production. I won't list them all, but there are a bunch of them. And now we're going to look at one or two of these. So let's look, for example, at the function for rendering macros. So it takes this mysterious LaTeX state thing as an argument, and also the payload, the name of the macro, that's the string, its arguments, that's the list of LaTeX expressions, and it's supposed to produce HTML. So here's how it's defined. It's going to be defined by another case statement. We first of all look up the name of the macro in a dictionary, a built-in dictionary. The keys are macro names and the values are rendering functions. If it finds an entry in the dictionary, then it applies that rendering function to the appropriate arguments, the LaTeX state and the macro arguments. Okay? If it doesn't find it, then it has to take a decision. And to do that, it looks up the name once again in another dictionary, LaTeX state.macro dictionary. So this is a dictionary that contains the user-defined text mode macros. If it does not find it, then it makes a little piece of HTML that says, okay, this is your macro and it doesn't exist, so you better do something about it. And all in red so that you can find it, okay? And if it does find it, then if it does find the macro definition, then it first of all creates a macro value, and it has the information for that because it has the name of the macro and the args, okay? It also uses a function macro.expand to expand that macro using the macro definition that it found, okay? And that gives you a LaTeX expression that can then be rendered, okay? The macro module, by the way, is only about 60 lines long. It's quite small, okay? So the beauty of functional programming. So in the time remaining, let me say a few things about the full parse render pipeline. It's a little more elaborate than I have alluded to. You begin with the source text, and then you use a finite state machine to split it up into a list of logical paragraphs. These are either ordinary paragraphs set off by a pair of new lines, or an outer begin-end pair for an environment also set off by a pair of new lines. The reason for that is that if you didn't do that, you could never properly parse an environment that was not a single ordinary paragraph. You then incrementally, in a way that I'll try to describe if there's time, apply the parser to generate a double list of LaTeX expressions. Okay, so you see if you parse a paragraph, that will give you a list of LaTeX expressions. Since you have a list of paragraphs, you're going to get a double list. And the LaTeX state is this still unexplained thing that has to be generated. Then you apply the renderer. You get a list of HTML elements. You need to join those to make an honest-to-gosh HTML element. You could do this in various ways. You could join them end-to-end with no space between, or you could join them with one space. Both of those are wrong because sometimes you want one, sometimes you want the other. So you have to develop another little abstraction and some rules to properly concatenate them. And you do that, and you get something that looks pretty good. You ship that off to the domain object model for the Elm runtime. MathJax says, okay, I see some math nodes. It renders them, and you're done. So that's the full pipeline. Looks like it might take a lot of time to do all that stuff, those 6 things. But as you saw in the demo, it actually operates quite quickly. So how much time do I have left?
Just about 5 minutes.
Okay, that should be enough. So let me say a few words about computing the LaTeX state. So this is going to be done using folds, one of our favorite FP constructs. A fold has as its first argument a function which I'd like to call a reducer. It takes an A to a B to a B. A typical application is let's add the numbers in a list using the function plus. We're going to get 10, of course. The function plus is a reducer of type int to int to int. 0 is the accumulator, the value in which we build up the final value. And then we have a list of inputs. Okay, so the way we're going to build up this LaTeX state is using something called an accumulator. So that's a little gizmo that accepts a state as input and a list of things and produces as output an updated state and another list. Okay? The key ingredient is the parse accumulator. It takes as argument a LaTeX state, which may be an empty LaTeX state. Okay? The point is to build a good one up. It takes a list of strings also as input. That'll be the list of logical paragraphs. And as output, it will produce this updated LaTeX state that we're seeking and the double list of LaTeX expressions, which is the thing the renderer can work on. Okay, so here's how it works. It's a fold. This is going to sound like another cheat. We're going to apply something called a parse reducer to this initial thing, the initial LaTeX state, comma, empty list, with the input being the list of paragraphs. But the good thing is that, so that's the reducer, that's the accumulator, that's the input list, it's a list of strings. Now here's the great thing. The parse reducer has that general type, form. By comparing, we see that A must be a string, B must be that tuple. So we now know the type of the parse reducer. And as you know from this game, once you know the type of a function, it makes it much easier to implement it. So there, once again, is the type. And here's the implementation. The first thing it does is it looks at the input string and it parses that using the parser that we've been talking about. Okay? Then it's going to, this seems like a cheat again, but I'll explain it. It's going to compute a new LaTeX state by applying a LaTeX state reducer to the result of parsing that we just got and the LaTeX state that it was given. Okay, so what does it do? It looks at the parsed input, say for the current paragraph. It says, okay, this is a section, so we need to record what its section number should be. We're going to update the LaTeX state with that, and that'll be the new LaTeX state. So it's not too hard to implement that. And then we return as value that new LaTeX state and the parsed input list augmented by what we just did, the parsed input. Okay. Well, that was a little fast, but there it is. That's sort of the basic outline of it. The last thing I want to mention is that one of the reasons that the editor works so fast is the following. Here's some text we're working on. I edit it and I get some edited text. Okay. I can compute the greatest common prefix of U and V. So that will be the, these are logical paragraphs. It's a sublist, okay? I can compute the greatest common suffix. And then U is going to look like AXB, and V will look like AYB. And if I render U, that has the shape A prime, X prime, B prime, I store that, and now I've made some changes and I want to render V. But A prime and B prime are already computed by parsing and rendering. So all I have to do is to parse and render Y, and that's some little tiny thing, so that's really, really fast. Okay, so that's it. The ingredients for this were an expressive type system. They told me I have to have a conclusion, so here it is. An expressive type system. So, formulating the AST was key. Formulating the notion of accumulators was key. You need a good system of parser combinators, which Elm has, and Elm is fast. So for me, those were the things that made the project possible. So thank you very much.